ever wished you could just like send information somewhere instantly,
Yeah.
like without any physical connection. It sounds like, science fiction, but this thing, quantum teleportation, it's closer than you might think.
Yeah. Yeah, it's really incredible. It's an area of research that has been making just incredible strides. And it all comes down to one of the most bizarre and counterintuitive phenomena in all of quantum mechanics, and that is entanglement.
Okay, so entanglement, that's where two particles are linked, no matter how far apart they are. So you change one, the other one changes like instantly.
That's basically it. They're connected. They act like a single unit, even if they're, light years apart. It's this spooky action at a distance, as Einstein called it, that makes teleportation even possible.
So how does it actually work? Like, are we beaming objects or people from one place to another? Like in the movies.
Well, not quite. We're not teleporting the matter itself. What we're teleporting is the quantum state of a particle. So think of it like this. Instead of sending the actual particle, we're sending like a set of instructions that perfectly describe its state.
So it's like sending a blueprint rather than the actual building.
Yeah, that's a great analogy. And once you have those instructions, you can recreate the particle's state in a completely different location using another particle that's entangled with the original.
That's incredible. So we're not physically moving anything, but we're recreating the exact same information somewhere else.
Exactly. And because entanglement allows these instantaneous changes across vast distances, the information transfer is essentially instantaneous.
This is blowing my mind. And this is actually happening in laboratories.
Oh, absolutely. Scientists around the world are teleporting information using all kinds of different systems, from photons, which are particles of light, to atoms, and even superconducting circuits.
So it's not just a theoretical concept anymore.
Not at all. In fact, researchers in China, they've successfully teleported photons across a lake over 100 kilometers wide.
Wow, that's like teleporting information from here to, well, a very long way away. But what about teleporting on a much smaller scale? Like, is that possible?
Absolutely. Scientists have also achieved teleportation between trapped ions, which are basically atoms that are held in place by electromagnetic fields that are just micrometers apart. Imagine the possibilities of manipulating information on such a tiny scale.
It seems like there's like a whole spectrum of teleportation.
Yeah,
From like the incredibly large to the incredibly small.
that's a great way to put it. And depending on the system, and what you're actually trying to teleport, there are different techniques and challenges involved. Like you have qubit teleportation, which deals with these discrete units of quantum information. And then you have continuous variable teleportation, which is used for things like light waves.
Okay, I'm trying to keep up. So we've got these different methods of teleportation, but it's all about transferring information, not matter, using the power of entanglement.
Precisely. And implications of this technology are just vast and far reaching. But before we get into those, let's explore some of the more fascinating variations on teleportation that scientists are working on.
Variations, this is getting even more interesting. What kind of variations are we talking about?
Well, one that's particularly mind-bending is entanglement swapping. It's like teleporting entanglement itself.
Entanglement swapping, what does that even mean?
Okay, so imagine this. Instead of two parties directly sharing an entangled pair, they each have a particle that is entangled with particles held by a third party. Now, if that third party performs a special kind of measurement, It's called the Bell measurement on their two particles.
Bell measurement. It rings a bell, but remind me, what exactly is a Bell measurement?
It's a way of determining if two particles are entangled. So it's like revealing the hidden connections between them. And what's amazing is that when this third party performs this Bell measurement, it instantly entangles the particles held by the original two parties, even though those particles have never actually interacted directly.
So you're essentially creating entanglement between two particles that were never entangled in the first place. That's
Yeah.
crazy. What's the point of that?
It's incredibly useful for extending the reach of quantum communication. Imagine creating like a chain of entangled particles where each link is established through entanglement swapping. You could like transmit information across incredibly vast distances, much farther than what's currently possible with direct entanglement.
It's like building a quantum relay race for information.
Exactly. And this leads us to another fascinating possibility, which is quantum teleportation networks. Picture a world where multiple parties can just seamlessly teleport information between each other, like a super secure and instantaneous quantum internet.
Whoa, a quantum internet. Now we're talking. But hold on, before we get too carried away with these futuristic scenarios, let's talk about the challenges. What are some of the hurdles we need to overcome before teleportation becomes, like, truly practical and widespread?
That's a great question. And it's important to remember that this is still a relatively young field. There's a lot of work ahead of us. One of the big challenges is fidelity. You see, teleportation isn't always perfect, and errors can creep in during the process, especially over long distances.
So it's like a game of quantum telephone, where the message can get garbled along the way.
Exactly. And that's a big problem, especially when you're dealing with, sensitive information. Another challenge is the need for robust quantum memories. To build a truly functional quantum network, we need a way to store quantum information reliably for, long periods.
So we need something like a quantum hard drive
Yeah.
that can, like, hold on to this fragile quantum information without it getting corrupted.
Exactly. And these memories need to be incredibly stable, they need to be resistant to noise, and able to store information without errors.
So error correction and storage, those are major hurdles. What else is, like, standing in the way of our quantum dreams?
The biggest challenge of all might be integration. We need to figure out how to make this cutting edge technology work seamlessly with our existing, classical infrastructure. How do we merge the quantum world with the world of like fiber optic cables, satellites, and the internet as we know it?
It sounds incredibly difficult, like trying to bridge two completely different technological universes.
It is. But there's been this recent breakthrough that gives us reason to be optimistic. Researchers at Northwestern University have achieved something truly remarkable. They've successfully demonstrated quantum teleportation over existing internet cables.
Wait, seriously, how did they manage that?
It was incredibly clever. They realized that all the data in optical communications is converted to light. So they carefully studied how light scatters within fiber optic cables and found like a specific wavelength of light that was less crowded.
Like finding a quiet back road amidst all the traffic on the information superhighway.
Precisely. And they then added like special filters to further reduce noise from all the regular internet traffic.
So they basically created like a dedicated lane for their quantum information to travel.
Exactly. And it worked. They sent quantum information and high-speed internet traffic through a 30-kilometer fiber optic cable simultaneously, and they found that the quantum information was transmitted successfully.
This is a game changer. Does this mean we're closer to that quantum internet you mentioned earlier?
It's certainly a major step in that direction. This breakthrough opens up a whole new world of possibilities for quantum communication without the need for, specialized infrastructure.
This is all so fascinating.
There are even more variations of teleportation that researchers are exploring.
Oh, like what?
Well, there's one called port-based teleportation. It's a bit different from the kind we've been talking about. It doesn't require any corrections to be made.
No corrections. That sounds much simpler.
Yeah, so imagine you have two people, Alice and Bob, and they share a bunch of entangled particles. Think of these entangled pairs as like ports. Alice performs a measurement on the particle she wants to teleport, along with all of her entangled particles.
So she's measuring like a whole bunch of particles all at once.
Exactly, and based on the outcome of her measurements, she tells Bob which entangled particle or port to hold on to.
Okay, and what about the other ports?
Bob just gets rid of them, and the fascinating thing is the particle that Bob keeps will, magically be in the same state as the one Alice wanted to teleport.
Whoa, that's incredible. And it sounds like a much more direct approach. So what's the catch?
Well, the downside is that it requires a huge number of entangled pairs, or ports.
Right.
It's a very resource-intensive process.
So maybe not the most practical method for like everyday use,
Right.
but still fascinating from a theoretical standpoint.
Precisely, it's pushing the boundaries of what we thought was possible with quantum information.
Speaking of pushing boundaries, we've been talking a lot about these different systems for teleportation, like photons and trapped ions. Are some systems better than others?
It's not really about one system being inherently better. It's more about choosing the right tool for the job. Each system has its own strengths and weaknesses.
So it's like a quantum toolbox, each with its unique purpose.
Exactly. For example, photonic qubits, those tiny particles of light, they're amazing for long-distance teleportation. They can travel through fiber optic cables or even open space with minimal information loss.
Makes sense. I mean, light travels vast distances across the universe. It's how we receive information from, distant stars.
Precisely. But photons can be tricky to control, and store trapped ions, on the other hand, offer incredibly high fidelity and long storage times. But they're difficult to scale up for long distances.
It seems like there's always a trade-off.
There often is in the quantum world. It's about finding the right balance for the task at hand, and then there are superconducting circuits. They operate at extremely low temperatures where electrical resistance vanishes, and they show real promise for building large-scale quantum computers.
So they're like the heavy hitters of the quantum world.
In a way, yes, and they've shown great potential for both high fidelity and scalability in teleportation experiments.
It sounds like there's a lot of exciting progress happening with all these different systems.
Absolutely, and don't forget about atomic ensembles. These are large groups of atoms that can store and process quantum information and are showing real potential for building robust quantum memories.
Quantum memories, that's like how long you can store quantum information before it kind of deteriorates, right?
Exactly, and atomic ensembles are showing promise for building memories with long coherence times.
These atomic ensembles could be the key to, like, reliable and long-lasting quantum storage.
They're definitely a contender in the race for building a practical quantum internet.
And speaking of contenders, I've heard whispers about diamonds playing a role in this quantum revolution. Is there any truth to that?
There is specifically, we're talking about nitrogen vacancy centers in diamonds. These are
Wow.
special defects in the diamond structure that can store and manipulate quantum information.
Wait, so those sparkly diamonds we wear on our fingers could hold the key to the future of quantum technology?
It's possible these nitrogen vacancy centers have shown remarkable coherence times, even at room temperature, which is quite remarkable for a quantum system.
That is remarkable. So we have photons, trapped ions, superconducting circuits, atomic ensembles, and even diamonds. It's like a whole quantum zoo out there.
And each species has its own unique capabilities and potential for shaping the future of quantum technology. It's truly an exciting time to be working in this field.
It sounds like the possibilities are like truly endless. But with all this incredible potential, let's not forget about the challenges that still lie ahead.
You're absolutely right. It's important to be realistic about the hurdles we still need to overcome.
So, like what?
Well, as we discussed earlier, fidelity is a major concern. Ensuring that quantum information can be transmitted without errors, especially over long distances, is a huge challenge.
So we need to, minimize that quantum telephone effect.
Exactly. And then there's the challenge of scalability. How do we build quantum networks that can handle vast amounts of information and connect users across the globe?
It's like trying to scale up from a small town to a bustling metropolis.
A very apt analogy, and we can't forget about the integration problem we discussed earlier. How do we seamlessly blend this quantum technology with our existing classical infrastructure? These are all complex issues that researchers are actively working on.
Sounds like there's no shortage of challenges, but also no shortage of brilliant minds tackling them.
That's what makes this field so dynamic and exciting. It's a collaborative effort pushing the boundaries of human ingenuity and scientific understanding.
And who knows what incredible breakthroughs await us just around the corner. Perhaps one day quantum teleportation will be as commonplace as sending an email.
Imagine a world where we can communicate instantly and securely across vast distances thanks to the power of quantum entanglement. It's a tantalizing vision of the future.
A vision worth striving for sure. But for now, I think we need to give our listeners a little break to digest all this incredible information. We've covered a lot of ground, from the theoretical foundations to the mind-boggling experimental implementations and the vast potential of this revolutionary technology. Okay, so I think it's time we address the elephant in the room, or, the question that's probably on everyone's mind. When we talk about teleportation, it's hard not to think about, all those science fiction scenarios where people are beamed from one place to another. So, will we ever be able to teleport matter the same way we can teleport information?
That's the big question, right? And while it's an incredibly captivating idea, the reality is that teleporting matter, it's just vastly more complicated than teleporting information.
Yeah, why is that? If we can teleport the quantum state of a particle, why not just scale things up and teleport a whole person?
Well, it's not simply a matter of scaling up. Remember, teleportation hinges on this entanglement thing. To teleport a person, you'd need to create an entangled copy of every single particle in their body.
Which is, not exactly feasible at this point.
Not with our current technology, no. We're talking about trillions upon trillions of atoms, each with its own unique quantum state. Creating and managing that level of entanglement is, well, just beyond our capabilities right now.
So teleporting people is still firmly in the realm of science fiction. For now.
It seems that way.
Uh-huh.
But who knows what the future holds? Science has a way of surprising us.
That is true. But even without teleporting ourselves across the galaxy, the potential applications of quantum teleportation are still just incredible. We've talked about secure communication, powerful quantum computers, and even the possibility of, a quantum internet. What other mind-blowing applications might this technology, unlock?
One area that's generating a lot of excitement is quantum sensing. Imagine sensors so sensitive that they can detect the slightest changes in gravity, magnetic fields, or even, time itself.
Sensors that can detect changes in time. That sounds like something straight out of a sci-fi movie.
It might sound far-fetched, but it's a real possibility thanks to the principles of quantum mechanics. And such sensors could revolutionize fields like, navigation, medical imaging, and even our fundamental understanding of physics.
It seems like the possibilities are truly just limitless. Quantum mechanics has a way of constantly pushing the boundaries of what we thought was possible.
It certainly does. It's a field that continues to challenge our assumptions and expand our horizons.
So, quantum teleportation, from a fantastical concept to a revolutionary technology, with the potential to, reshape communication, computing, sensing, and our very understanding of the universe.
Yeah, it's been an incredible journey exploring this fascinating topic, hasn't it?
It really has. And for anyone looking to kind of continue their exploration of the quantum realm, I might suggest Blast Off by Cyclona. It's the perfect soundtrack for contemplating the mysteries of the universe.
Excellent choice. It's a track that truly captures the awe and wonder of scientific discovery.